in a biology lab, 50,000 bacteria are growing in a petri dish. The number of bacteria in the dish needs to be decreased to 100 within 30 hours. You add some antibiotic solution to the dish and the bacteria begin to die. After 5 hours, the number of bacteria is 30,000. Determine the constant K to the nearest 10,000. So, first thing you need to remember about this is that it comes from the formula N equals N naught E to the RT. KT. So determine the constant K to the nearest 10,000. Got to plug in what we know and solve it out. So N naught is the starting number. We're starting with 50,000. We're solving for K, so we obviously don't know that. N is how much you have after a certain amount of time. So we know that after 5 hours, it's down to 30,000. So 30,000 is the amount that's left after a certain amount of time. And that time is 5 hours. So plug that in for T. Now we're going to solve for K so we can then answer part B, which is write the equation. So to solve, you first have to get, we're trying to solve for K, so we need to get E to the 5K alone by dividing by 50,000. All those zeros cancel out, so we get 3/5 equals E to the 5K. Since we're trying to solve for an exponent, we're going to log both sides. So natural log. Natural log of E cancels out. So we have 5K equals natural log of 3/5. So now we'll use our calculator to get natural log of 3/5. Make sure you put parentheses around it just to be safe. Natural log of 3/5. So there's that number. To solve for K, we still need to divide by 5. Divide by 5. So this number, negative 0.102, is K. Since we're going to need that later, store it as letter K. Store it for variable K. That way, when we type it into the equation later, we can just use K rather than typing out all 12 digits or whatever that is. So on our paper, we're going to write down that we got K equals negative 0.102 approximately. Oh, it says to the 10,000th, so we need one more decimal point. Next decimal point would be another 2. So now it's to the 10,000th. Write the particular equation for the number of bacteria in terms of time. The number of bacteria starts at 50,000. E to the K, which is negative 0.1022. Times T. When it says write the particular equation, that means using variable N and using variable T. That's your equation. Just like y equals mx plus b is your equation. You're going to have two variables in it. How many bacteria will be alive in 15 hours? That means using this equation we just wrote, plug in 15 for t. So 50,000 times e to the negative, or e to the k times t, which is 15. E to the k times 15. I'm just writing k here because we're punching that into our calculator and we're going to use letter k because we stored it for letter k. I need e to the kt. For k, we can use k because we stored it. For t, we're using 15 because it said 15 hours. There's e to the kt times 50,000 because that was the number in front of e to the kt. So there will be 10,800 left. After 15 hours, there's still 10,800. According to this model, will this antibiotic solution reach the goal of decreasing the bacteria to 100 in 30 hours? Show your work, justify your answer. So 30 hours, very similar to what we just did in the part right above. We're going to plug in 30 now. So it starts at 50,000, e to the k times 30. And we want to know if that gets down to 100 bacteria like it's supposed to. So e to the k times 30. Times 50,000 because that was the number in front. No, there's still 2,032. Oh, 2,332. Oh, did it get down to 100? No. Doesn't reach goal.